you can just unmute yourself. After today, I will just broadcast the lectures in case you don't want to come here. But still, always better to come if you can. Okay. So the idea for today is we're going I'm just going to start with what a topology is supposed to be. And we're going to motivate that with examples afterwards. So let's start with just with definitions. So this is lecture 2. Today we're going to see topological spaces. Just definition, maybe some examples. So this is chapter 12 in our Micros textbook. So let's start with the definition. I'm just going to tell you what a topological space is. So definition 1, usually I number my environments lecture-wise. So I'll have like, definition 1 for today. So topology, this is what I'm defining. On a set X is just going to be a collection of subsets. How far do I want to go? It's a collection of subsets. Let's call this collection. This is either a tau or a calligraphic T. So a collection of subsets of X, which means a subset of the power set. So subsets of X, such that 3 things. The first one is the empty set and the entire set are elements of this T. So the 2 trivial subsets are always elements of your T. The second one is this is what's called T is closed under arbitrary unions. So how do we write that? If we have a collection something like, let's call this U sub alpha, where alpha is some index. If we have a family of elements inside of T, then also their union is an element of T. So what I'm saying here is you take arbitrary unions of elements in T, you should still be in T. And the third one is if we have a particular case here of lambda having 2 elements. So if you have U1, U2 in T, then their intersection is in T. Yep.
The one that's confusing is the first one. So it's tells about subset and power set such that X and the empty set is
right, both. Yes, empty and X. Maybe let's be more clear. Empty is in T, and X is in T. Yeah, there you go. And then this is what the topology is. So if you're wondering, why should I take this class if that's what a topology is? Well, I need to convince you this is a useful notion. That's what's going to happen in the next couple of lectures. So in this case, the pair X comma T, so it's a set with a topology. This is called a topological space. A topological space can you read this? Is this big enough? Do you want me to do something about my handwriting? Are we okay? So this is a topological space, and arbitrarily, we say that elements in T are called open sets. So what did I define here? I defined the notion of topology. I defined what a topological space is, and I defined what open sets are. Yep.
This is a really basic question. That's why we clarify that the power set is like, if you have a set of elements, the power set is all of the groupings, right? All the tuples of those elements, right?
Absolutely, yes.
So if that's what the power set is, and we're taking a subset that has both the empty set and one element with all, or sorry, the empty set and each individual element of X.
No.
Oh,
So power sets of X is any subset of X. So D, where D is a subset of X. This is the power set. So here you always have kind of trivially the empty set, and you always have here the entire space.
is that true for so every power set, X is a subset of every power set?
X is an element.
An element of every power set. So,
But X is not an element of any power set. It's an element of the power set of X.
yeah, so the first condition for a topology is kind of trivial because that's true for any. I guess it's true for any power set, but not any subset of power set.
Right, but the crucial thing is this guy. So I'm not going to take an arbitrary collection of sets. I'm taking some very particular collections. And on those are called topologies. So yeah, these are not arbitrary. These are collections of sets with some properties. Are there any other questions? Yep.
The third condition, like, is that if you,
So this is kind of a set, U alpha.
I mean, the one below that is a U,
U1, U2.
U1.
Yeah.
So what does that say? It says that U1, U2, and T, then.
Their intersection is in T.
Is that a 2 or it looks like a U, lambda, capital lambda?
U1, U2.
Oh, that's fine.
Yeah, sorry about that. Yeah.
I have no question. The definition you use for two, if U alpha and alpha is an indexing set, so all that is like U1, U2, like that's what alpha means for you.
But I want to be clear that the indexing here could be anything. That's the important thing about part two. It can be anything. Any other questions? Okay, so kind of immediate thing I should say, remark here. So if you have for any collection of sets of subsets of X, this condition 3 here, this condition is equivalent to this more general one. Let's call it 3 prime, which says if you have U1 all the way through some UN elements in T, then also the intersection from 1 to N of UIs, also an element of T. So here N is supposed to be any positive integer. And positive integers we denote by method BBN. Yep.
I'm a little confused. Is that if UN dot UN like
U1.
U1?
So for 3, that means that it has to be a finite number of intersections.
Absolutely. So these things are called arbitrary unions, and these are called finite intersections. So here we're saying T closed under arbitrary unions. This is what 2 says, and this guy 3 primes says T closed under finite intersections. And that's how you remember what the topology is.
The inverse of an element in T are called open sets. Is that like a definition?
Right.
Is that a conclusion?
No, that's a definition. There's no way for us to conclude anything here, just defining stuff. So everything here is a definition. This is definition. Okay, any positive integer. And yeah. So how do we prove this? I'm not going to give you a proof, but let's say 3 prime absolutely implies 3, because just take n equals 2. And then 3 implies 3 prime. This is just an exercise for you. And I want you to remember how to use induction. But that's usually how you go from 2 to finitely many. So you should prove this by induction on n. Okay. Let me continue up here because cameras are pointing this way. Can you read that? Okay, now examples. So maybe the first one I want to do like general stuff first. So general stuff is good, but then also not very instructive. So for any set X, we can take just condition 1, kind of. We can take the family or the collection that I'm going to call T triv, because it's only going to contain the 2 trivial subsets. So this is a family of subsets of X. This is always a topology. On X.
That's it.
Triv
True.
from trivial. Triv. It's a topology on X. This is called the trivial topology. So here we should verify it's actually topology, but let's not write that. Let's think about why that's the case. So of course, 1 is true. That's how we're defining tau triv, just putting these 2 subsets. And then 2, if we take a collection of subsets in T triv, then the union, they're either empty or X. Then the union is either empty, depending if the set you took is just the empty set of X, if there is some X in that collection. So the union is, of course, going to be something in tau triv. And then finally, part 3 is the same. If you intersect some empties with some entire space, you either get empty or entire space. So we're safe here. Do you agree? Yeah.
Well, from what you just explained, theoretically, in this case, tau could just be the power set, right? Or
This is an example. I'm defining a topology. That's the next example. For any X, or any set X, now the family that I'm going to take is going to be T discrete. So just this. This is the entire power set. It's also a topology. And this one is very easy to verify. Of course, the empty set and the entire set are both subsets. And if you take unions, you're still a subset. If you take intersections, still a subset. So this is absolutely clear. And this one is called the discrete topology on X. So these two are not that interesting. For the second one, every subset is open. And we don't really know why yet, but open sets should be special. These are the elements in our topology. They should be special. They should help us measure something. Something should be nearness. I need to convince you of that. But if everything is open, everything is near to everything else, and then that's not a very interesting thing we could do. Any questions?
So for these, you just verify the three
Right.
properties.
But I'm not writing them because I think it's not that instructive, but we should.
Yeah.
So another example, let's do number 3 here, and then we'll do an interesting one. So let's take X to be just set with 3 elements. And I'm going to do like 3 different drawings here. Here's my first X, A, B, C. Here's my second one, should be identical, A, B, C. And there's the third one, A, B, C. Now I want to draw here 3 pictures. In each of these pictures of X, I will identify some subsets. So for the first one, let's identify, I don't know, something like, let's take this subset containing A and B. And let's take this subset containing A. Do you understand what I'm doing here? So is that collection of subsets a topology? Is it or is it not? Any guesses? This is a very good moment for you to be wrong, because the first example you're saying here. So the empty set, let's say it's there, I cannot draw it. So let's say the empty set is there. And let's say I'm also taking X, the entire thing. Is this a topology?
Saying one of them is an empty.
Right, I'm also assuming there is always the empty set there. I cannot like draw it, but let's assume it's always there. Is that a topology? So part 1 is for free. I'm including empty and X.
The intersection.
Right, the intersection, so that will be part 3. So here in this one, the first one, let's do this tau 1 is empty, X, singleton A, and then A, comma B. That's my T1. This is absolutely a topology. You intersect non-trivial things like these two, then you get A. If you compute the union of non-trivial things, you get AB. So this is a topology. Let's do something here. Maybe let's do AB and BC. So here for my T2, I'm taking NT, X, AB, and then AC. No, BC. Is this one a topology? We are okay with non-trivial unions, because if you do the union of these two guys, you get the entire X. But we're not safe with intersections because these two guys intersect at the singleton B, which is not here. So not a topology. But we can like fix that. Let's take these two, and then let's also take the singleton here. So this is empty, X, AB, BC, and singleton B. And this one is a topology. So of course I cannot, in this example, I cannot do anything about arbitrary unions because we only have like finite amount of subsets. So at most I can do finite unions. But our sets X are pretty much never going to be finite. Do we have any questions? Yep.
You repeat the second one, so we take the intersection.
So this one is not a topology because if you do AB intersection with VC, what you have is B, the singleton B, which is not an element of T2.
It's not the power set.
It is in the power set. It's not in this particular sub-collection of the power set.
Oh, I see. So tau is not just a power set.
Oh, no,
It's
no.
a subset of it.
Right. The power set is absolutely not interesting. That's this example. It's something that's there. It's a topology, but it's a very non-interesting topology. It's not going to help you measure anything. I need to convince you of that. That will happen at some point. You'll see that's not very. It's not a very useful topology. Yep.
So far, we haven't really had something where verifying 3 would be, because to verify 3, you would need like because right now all the subsets are just like 2 elements. Like to verify 3, you would like take the intersection of like the intersection of A, B, and B, C, but right now that's just one thing, right? Like so far we've only verified 2, but how would we verify 3 for like T2 for example?
No, here I'm verifying 3. It's actually not true. Right, here it's not working, but I tried to. And here, same thing. If you intersect these two, then you have B, which is an element. If you intersect these two, then you have B, which is an element of T3. If there's a first and last one, also true.
Yeah, so you have a big set, power set, I guess, or, sorry, a big tau.
Mhm.
You just use induction for 3.
For
3 prime, 3 prime. I mean,
right, yeah, 3 prime is
it's too general, and you just use induction to prove the intersection is. Is this one of the units?
oh, you mean if the set is bigger than 3 elements?
It's very easy with just taking the intersection.
No, yeah, but I to be honest, I don't want. I just want here when I'm doing illustrating stuff. I never wanted to think about these sort of topologies. These are only good for certain counterexamples, but this is not an interesting space. A thing with 3 elements is never going to be an interesting space for us, at least. Any other questions? Okay, so now let's. Maybe I want to say something else first. Can I do 4 over here? Let me do 4 over here. I'm sorry, but I want to use that blanket for something else. So example 4. Again, for any x, that's very good because I have general x here. For any x, this collection that I'm going to define now, it's called T sub CF. And this is going to contain all subsets of x which have finite complement. So such that x minus u is finite. Is finite as a set. And I also want to throw here the empty set because x might not be finite. So here I need to formally add the empty set. So I could say x minus u is either finite or the entire x. And I don't need to do this weird thing. So this is also a topology. This is called is a topology. And this one you will have to verify on homework. This is called the cofinite topology on X. The cofinite topology on X. And that one can be interesting. We'll maybe think about that later on. So here open sets are sets which have a finite complement. So their entire space, but some finite amount of points. So before we keep doing weird things, I want to give you a motivating example. Can everyone read here? Can everyone read here? Okay. So motivating example. So this is what's going to be called the standard topology on the set of real numbers. Could also be any other like Cartesian space R to the something. So maybe let's start with notation because I want to use this. So if you give me some real number x and some positively real, let's call it epsilon, I'm going to denote by b x comma epsilon all real numbers which are a distance at most epsilon from x. So this is just the interval x minus epsilon, x plus epsilon, open interval. So of course I could say r to the n, and I could use my general distance here in r to the n and keep the same notation, but for us this is just an example. We'll do that later. So here I'm going to define T standard. This is going to contain subsets of the real line with this particular property. For any x in U, there exists some positive epsilon such that this interval or this ball centered at x is a subset of U. So this is a thing on the real line. These are particular subsets of the real line, but you should think of this as something like, here's my U. And what I want here is for every x in U, I want to be able to draw some kind of open ball that's going to be contained in U. If you get kind of closer to the boundary here, this radius should go smaller. This epsilon should go smaller. But if you hit the boundary, you are in trouble. Because that thing is now outside of U. So what you actually want to do is, instead of doing U like this, you need to keep your U open. You don't want it to have any boundaries. So think of this kind of maybe a sphere, but you don't want the shell of the sphere. Just want what's called the interior. That will make sense for us later. Do you see what I'm doing? So we'll see more examples of this. That is just a picture. I don't expect you to understand what's going on there. Sorry, camera's doing weird things. There we go. Okay, so this is T, yeah.
I just want to clarify kind of what this means. So what you're saying essentially is you have some tau, and that's the larger thing, and you're taking a point and you're taking an arbitrarily small, you're creating point x, you're taking arbitrarily small x epsilon, and that's like your radius, and you're shrinking that, right?
Kind of, but not exactly. So what's going on here is first I'm defining a collection of subsets. So I want to define this collection of subsets. Which subsets I'm going to take? I'm going to take subsets U doing something. And the something is this very deep thing. So this is not an easy example by any means. Here, I'm only going to consider subsets of the real line with this property. Whenever you have a point in your set, you can always find an open interval, maybe small, inside the set. If you have the set, you have a neighborhood, an open neighborhood of the set. So I'm using words that we don't know what they mean, but that's the idea. Yeah.
Okay, so what that means graphically is with the open neighborhood is that any point in the set, you can draw that like dotted circle around it, and that wouldn't be the case if a point was on the boundary of the set, because then the open circle would leave the
Absolutely.
opening.
Absolutely. Is that clear?
Just to finish, you would be on a closed If you're on the boundary, then that open circle is not an open circle anymore because it's on the boundary.
It's going out of you.
It's coming out in.
Right.
If you include the boundary though. Oh,
So
you're saying that the point is on.
The moment you have a point on the boundary, whatever that means,
Draw any-
right, you can, but it's going to go outside of the space. So you could, but it's not going to be good. So those things shouldn't be open. They are subsets, but not open. Okay, so now we should verify this is a topology. So let's verify. Verify 1, 2, and 3. So this is a topology. So part 1 here, it's clear that empty set is here because this is always false. So it's kind of clear that empty is in T, and also the entire X, and also is in T. Right, so for the real line, you just take, for any X, you take any epsilon, and you're done. Given X in reals, take any epsilon, for example, epsilon equals 1. Okay, so number 2 now. I need to take an arbitrary collection of elements in T standard. So let UI, where this I is an arbitrary index, be a subset of collections in T standard. And now we want to show, so I'm going to use this a lot, want to show the union is also there. So union over this big family of UIs is also in T standard. So how do we show such thing? How do we show this? This is what we want. I need to go to my definition of T standard. Right? I need to go over there. So here I only include sets, subsets with this property. So I need to verify that this guy satisfies this property. If I'm going to show this set satisfies this property, I need to start with an arbitrary X in that set. So let's take an arbitrary X in the union. And I want to find some epsilon that's going to be inside the union. What can we do here? This is an actual proof. We're working on our first proof. We need an idea. So what we want, let me write here what we want. We want epsilon such that this ball center X radius epsilon is inside the union. This is what we want. Terrifying. What can we do? Yep.
And you just say, like, if the element is inside the union, it has to be inside one of the sets.
And then we're pretty much done because of the definition. That's right. Since X is in the union of these guys, we know that X needs to be in some of them for some J. Right? Definition of union. But now that this guy, this is not an arbitrary set, it's an element here. So let's write that. Since uj is in this T standard, we know there is some epsilon for which, can you read over here? I'm going too low. Just too low, right? Okay, let me see. How can I fix that? Let's continue over here. Oh. Yeah, I'll need to move the screen. Okay, I cannot say that, but thank you. Okay, so such that the entire ball center x radius epsilon, ball center x radius epsilon is inside this uj. And that's because uj is in T standard. I'm just using its definition, the definition of T standard. Right? But now we're done because this entire guy is a subset here. This is a subset of the union. So we're done. Are we okay? So I will write things properly because this is our first proof, but we're done. So since uj is a subset of the union, we also have that this ball center x radius epsilon is a subset of the union. And this is what we want. So I took an arbitrary x in the union. I show there's an epsilon for which the entire open chunk is inside the union. Yeah.
So along the logic, I get everything up to then you say since UJ is in T as standard,
Mhm.
there's stuff that, like, how can you go from, we know X is in UJ to therefore use J of J is in T standard?
Oh no, because of this. This is, you don't show that an arbitrary union of anything is in T standard. You show that an arbitrary union of elements in T standard is in T standard. So each of these guys needs to be in T standard. That's what I'm saying here.
If I'm thinking, once we say that X is an element of U sub J for sub J in sigma, all right, sorry,
Mhm.
lambda. And then we say since UJ is an element of T standard, how did we get that? Is that just by definition of T standard?
Because of this. Every element here, every UI is in T standard.
That's a given, okay.
That's what I'm saying here. I have a,
Then we say there's some epsilon greater than 0 such that, how do we get that X part?
that's the definition of T standard.
Okay. Okay, got it.
So here it seems that we're doing something, but the only thing that we're doing is mostly logic. We're not really doing much. You will understand what's going on. I don't know if later today, because I don't know yet exactly what's the pace of this class. But we'll see. The way we are defining this T standard is very friendly. It's kind of cumbersome, but then when you want to prove stuff, it's very friendly. Yeah.
I propose that we like change the diagram of U to be like more than one ball. Like, have like at least a couple.
Oh yeah, that's absolutely great. Yeah. So, and if one blob is not good, like this, then you are not good. Absolutely. Yeah.
Wait, I don't follow.
What he's saying is, okay, this U is good. That U that you have here is good. And remember, you want your T standard to be closed under unions. So if you have two blobs with no intersect, that still should be open. And that's absolutely true. That's absolutely true. No, not really. Just because if this guy is okay, and now you take a different copy of the same guy, kind of here, then the union should also be okay.
Oh,
And that's what we're doing. Yep. So that's 1 and 2. Now I need to verify 3, which is what I'm erasing now. So to verify 3, I need to take just 2 of those, 2 elements in T standard, and I need to verify also the intersection is in T standard. So part 3, let U1, U2 in T standard, and now we want to show that the intersection U1 intersects U2 is in T standard. So how do we show such thing? I need to take definition of T standard means I need to take an arbitrary element in that set. And what we want, then we write what we want here. We want to show that there is some epsilon such that the entire ball or open interval is inside the intersection. U1 intersects U2. This is what it wants. For that arbitrary x, I need to find some epsilon. Okay, so what's going on here? What's going on is something like this. Here's my U1. Here's my U1. Here's my U2. Maybe that's too small for me. U1, U2. Here's my x. There is a ball here because of U1. There is a ball here because of U2. But maybe neither of those balls is going to work for the intersection, but we can shrink it, right? We have a ball for U1, have a ball for U2, but maybe neither of those balls is going to work for the intersection. But that we should fix. Are we okay?
We need to increase epsilon.
Well, decrease. Is that right? We have two balls. This piece of this ball is going out of U2, and this portion of this ball is going out of U1, but we can shrink it. So we need to shrink those epsilons. But let's write what we know. Since x is in U1, which is in T standard, we know there is some epsilon. There is some epsilon1, epsilon1, such that, okay, not so happy. There is an epsilon1 such that Bx epsilon1 is inside U1. Definition of T standard. Yep.
We're not saying that necessarily the epsilon is too big, but because it's arbitrary, it could be, and we want to show that it always is going to not be too big.
Right. We need an epsilon doing something. And we have two epsilons. We don't know if they're good or not, but we could fix that. So since x is in U1, we have something. Since x is in U2, we have some other thing. Exists epsilon2 such that now centered epsilon2 is inside U2. But now if we take smaller epsilon, now if we take epsilon to be the minimum between these two guys, are we going to be okay with that? What do you think? If we take the minimum, are we safe? Minimum between epsilon1 and epsilon2. That's going to work, right? Why? Well, just because epsilon is smaller. If we do this, then this ball at center epsilon, this is going to be a subset of epsilon1 because the radius is smaller than or equal to, and it's also going to be a subset of the other ball because epsilon is smaller than or equal to epsilon2. Yep.
That's correct. So we know, given the definition of T standard, that there is epsilon1 that works for U1, there's epsilon2 that works for U2, and whichever one's smaller, it already works for U1, and U2 is bigger, then it's going to work for both of them and vice versa.
Maybe you should say if U2 is smaller, but yeah. Oh, right. If it's bigger, yeah, it's also going to work for free. Otherwise, you need, yeah.
Real radius If that's one, if you give it on the radius right.
Right.
And it's smaller, then it's gonna work. But
Mhm. That's what we're saying. So this ball is inside of the first one, inside of the second one, but first one is inside the first intersection. Second one is inside the second one. Right? And we're done. Okay, so this is the topology. That's great. We have a first non-trivial topology. How do you feel about this? So if you ever wondered what's so special about open intervals, well, it's kind of this. They have this property. Now, let me mention, we are not really using exactly what these guys are. If you notice, that's why I'm using the notation here. We're not really using what these guys are. Notice here, I'm just going kind of formally. That's my definition. And then I never use the definition of this guy again. I just use something very particular, kind of this. I know they behave like this. And that's pretty much all I'm using. If you have two such guys, you can always find a smaller one inside the two. That's the only thing I'm using. So this is the crucial part of the argument. Everything else is kind of independent of what these B's are. Do you follow what I mean? That's an important thing to notice here. Okay, so that was a good example. I call this a motivating example. Hopefully it motivated you. So now the question is, how good is this notion? Or maybe let's say this T standard we just introduced at measuring nearness. Let's write that here. Remember, that's what we're supposed to do with topology. We should be able to gauge nearness. So we should understand if we're doing something good or not. And in the real numbers, we understand the notion of nearness. So for example, we really understand that. Recall, let's just stick with sequences. The sequence, let's call this xn, where n is any positive integer in the real numbers. A sequence is said to converge to some given x if for any positive epsilon there exists some big n such that if n is bigger than or equal to n, then the terms xn, x minus xn, let's say, is more than epsilon. That's how you define limits for sequences. And this is telling you xn is in this ball. For each epsilon, for each ball, at some point the sequence will live there. So the exercise I want to give you now, I want you to check, or maybe let's say prove. Remember, we denote this by xn converges to x. Prove that this happens if and only if for any u in T standard such that x is in U, there exists some big N such that xn lives in U if n is bigger than or equal to your capital N. So this is telling you a sequence will converge to your X if for each open that contains X, the sequence will eventually be inside that open. That's what we're saying here. And this should convince you, well, this T standard is actually measuring stuff. It's a really good notion to decide when things are near. Do you understand what you're supposed to do here? So this shouldn't be that complicated because we're just going from this expression that you knew from before to these new opens. But this is not an any open, it's an open containing X. So you know there is an epsilon. And then you're done. And the other one I want to show here is another one is each, maybe I don't want to use B epsilon, X epsilon, maybe let's say BY radius is in T standard. So here we're kind of using open balls to define the opens. But what I'm telling you, well, the open balls happen to be open. So if you take anything here, what I'm saying is if you're inside the ball like this, so this is what balls should be, right? So this is center at Y and radius R. If you take any element here like this, then there is some small ball that's inside of it. That's what I'm saying. No, because now your new X is not in the center of this guy. It's somewhere. So the radius should be defined using the epsilon here should be defined using this radius and the distance from X to Y. Are we okay? So this is kind of fun things you can do. Oops, light. Okay, so things I should say before you leave is, oof. Okay, so definition 2, this is not an example anymore. Definition 2 if you have a topological space, so notice I'm not even writing the topology now. So the first thing I want to define is a set C inside of X is closed. This is what I'm defining. And closed would just be complement of an open set if X minus C is open. Second one, we say that a set N of X is a neighborhood of some point, small x in X. Maybe let's use A here. It's a neighborhood of A if there exists an open U with X in U inside N. So for example, your N could be something like this. Points over here are not good for your N. So N is not going to be a neighborhood of these guys, but it's going to be a neighborhood of these guys. So let's do some examples. So examples over here. This is just terminology. And by the way, neighborhood are not defined in the textbook until chapter, I don't even remember, like 17 or something. Probably even more. So example, in the real numbers, when I don't say the topology in the real numbers, we always consider the standard one. In the real numbers, we have some things. First one is these intervals. The interval AB is open. You need to verify that. It's an element, it's T standard. This is also true for semi-infinite open intervals. So this and this should be B probably. Also, these two guys are open. So if you're convinced of this, then this is just because these guys either the same argument or union of these guys. Just let A go to like a negative integer. And then this closed interval, is closed. And that's just because, so here we can give an argument because the complement of this guy is just negative infinite A union B positive infinite. And this guy is open. This guy is open. So union of open is open. And then lastly, these guys, semi-open, and this guy, AB, neither open nor close. Okay, we're late. So let's stop here. Let's stop here. I will see you next week. And hit stop if you have questions, can answer those.